Okay, good afternoon, students and professors. I'm really truly honored to be invited to the National Cheng Kung University to deliver the talk. Actually, I've known National Cheng Kung University, many years ago. In fact, one of my uncles actually graduated from here. So today's topic is on ammonia as a potential energy vector for the future energy application. So my name is Dr. Chai, okay? Chinese name蔡伟翔, okay? So a little bit self-introduction on myself, okay? I graduated 2012 and in 2017, bachelor's and PhD in engineering at University of Nottingham, Malaysia. And I did 2 postdocs in China. And I'm currently the assistant professor in the at National Sun Yat-sen University, okay? Started about 2 months ago. So this is today's outline. So we'll first cover on the energy and environmental issues, and then we'll touch a little bit on the shipping sector. And after that, we will go on to the hydrogen and ammonia, which is today's focus, and the limitations of the ammonia systems and some relevant strategies, and also the ammonia, hydrogen, ammonia, methane, one of the strategies. And lastly, we'll cover on the summary and future perspectives. So I'm not sure how many of you have known National Sun Yat-sen University. Does anyone of you know National Sun Yat-sen University? Some of you graduated from there. Okay, good. So National Sun Yat-sen University is actually a university with a very nice, beautiful beach view. Okay, if some of you hasn't been there, okay, this is how it looks like. Okay, but okay, there's always a but. NSYSU is originally a zoo. Yeah, it is actually a zoo. Okay, I only know it after I've arrived at the campus. So we actually coexist with the monkeys on campus. For those of you who have graduated from NSYSU, I think you might have known, okay, our famous senior, okay, the monkey. So the monkey can basically infiltrate all parts of the university. It doesn't matter. So if the professor's room is not locked, basically you can encounter a monkey there. But why bring up a monkey when today's topic is on ammonia or energy? So today we will talk about this coexistence. Okay, coexistence. So we'll touch on that later. So just bear with me for a while. So energy is actually a very important issue. In fact, it's one of the top 10 issues in globally for this past decades. So conventional fuels is actually a major energy generator throughout, I think, throughout the human history. Or in fact, now conventional fuels is the major energy generator. So what happens is that, like what Professor Wu mentioned, Taiwan is actually used a lot of the energy is actually derived mostly from the conventional fuels, and conventional fuels here are mostly carbon-based. So the carbon-based energy, actually, this issue is not only affecting Taiwan alone. For example, Malaysia, for example, China, for example, worldwide. Okay, for example, during this Ukraine war. Okay, just because the Russia cannot transport enough energy over to the European countries, basically the European countries are, well, the energy, there's a very big, huge energy crisis over there. And with the increased global worldwide population, industrial processes will increase, and therefore increasing the global energy demand. This is like a chain reaction. We have more humans living on Earth, more industrial processes, and also definitely the global energy demand will increase. And no matter how hard you try, you still need energy, correct? And basically, there are three things in life currently. for example, youngsters, okay? First is electricity. Second, electricity, and also Wi-Fi, and also water. So one of these is missing. Basically, you are doomed. Okay, basically you cannot do anything without electricity. You cannot carry out experiment without Wi-Fi or without connection. You cannot do anything. Okay, so the graph here shows that actually, okay, we have this is the carbon emission graph. So we can see that the United States here, okay, United States here is actually quite consistent, their carbon emission, because they have been actually controlling very, very hard in a way. And Europe and Central Asia and East Asia and Pacific. So basically we know that the Asia region itself, the carbon emission is actually growing since the 2000s. You can see that the 2000s, they actually increased very rapidly. So this is the total carbon emission throughout the entire world. So when we have energy problem, then we have global energy demand. The increase in global energy demand will lead to the huge carbon and greenhouse gas emission. So the huge carbon and greenhouse gas emission actually also lead to very serious environmental and pollution issues. So one of the most harmful greenhouse gas is the carbon dioxide. The carbon dioxide alone stands for 74% of the total GHG on Earth. And alone, it contributes to about 30% of the warming potential, just carbon dioxide. So that's why countries worldwide, okay, try to come up with a lot of strategies to tackle with the carbon dioxide problem, or in fact, they will just term it as a carbon emission. So from this graph here, okay, I think it's 2017. We can see that huge population. Let's say, for example, China. China has a top population on Earth. So China, as well as the industrial. So they have very human and also heavy industrial activities. That's why you can see that it contributes to the most greenhouse gas emission on Earth, and followed by US and India, and then the EU region. So the Asia Pacific region. So then you might say, oh, it's just China, right? How does it concern us? But don't forget, we are also part of the Asia Pacific region. Taiwan is also Asia Pacific region. And place where I come from, Malaysia, is also Asia Pacific region. Asia Pacific region alone contributes more than 50% of the carbon emission. 50%. Just one region, more than 50%. And with all this carbon emission, global warming, we actually face a very, very huge problem due to the sea level rise. So this sea level rise actually caused Shanghai and Jakarta to sink, okay, to sink, because they are very vulnerable to the sea level rise, so they're actually sinking. In fact, Jakarta, about 2 to 3 years ago, Jakarta is already, the capital of Indonesia has relocated to Nusantara, okay, somewhere around here, this region. So the capital of Indonesia is no longer Jakarta. So next time when they tell people, when you go to Jakarta, the capital of Indonesia, so no, it's no longer there. It has already moved to Nusantara. But the thing is that, can you see the impact? The impact. Because of the sea level rise, Jakarta has actually the central government has already decided to move the whole Jakarta to the capital to Nusantara, and also Shanghai. Shanghai is also one of the highly populated city worldwide. Is also sinking. So that comes back to us. What about Taiwan? Correct. Most of the cities, these two cities, Shanghai and Jakarta, are actually coastal cities. if you know what is coastal city, basically it's very near to the sea. So, for example, just now you can see NSYSU is just beside the sea. What if the sea level rise happened to us? Okay, so I did a very simple test. So this is the Taiwan map. Okay, I guess I'm correct. Okay, I just extracted from the online. Okay, so this is the Taiwan map without any sea level rise. Without any sea level rise. And this is the figure of Taiwan map after 7 meters sea level rise. Just 7 meters. Okay, so the first impact, okay, since we are in the southern region, so the first impact you will see around Tainan city here. Okay, Tainan city. You can see the whole region, the blue color region here, is actually flooded with water. So this whole region no longer livable. It's no longer livable. Okay. So if I'm not mistaken, this is the place where with the famous salt lake. Okay. So basically, we will lose this place to live anymore. And then the inner city here, slightly inner city, and Tainan is actually very close to the sea. Tainan, Kaohsiung, all is very close to the sea. And then you can see that here in Taipei here, it's also actually flooded. Okay. It's not only affecting the sea coastal city, but also the inner city, let's say, for example, Taipei. So this actually ring a very big alarm to all of us. To all of us, actually a lot, if you can see through the history, okay, for example, in Malaysia, Malacca is one of the coastal city as well. So if Malacca is down in the sea, that's also, we cannot actually live there. So same goes to Taiwan. So actually a lot of the places are affected. So now we have already finished covering on the energy issue and also environmental issue. So today the topic is still on energy sources. So the conventional energy normally are non-renewable. For example, oil, for example, coal, for example, natural gas. Okay, so nuclear energy is also considered non-renewable. Oil, coal, and natural gas are actually carbon-based. And then for renewable energy, we have the wind, hydropower, solar, geothermal, and biomass. So for oil, coal, and natural gas, if you all know, the formation is from the so-called dinosaurs, okay, millions of years ago. But if you deplete the reserve, the oil reserve, basically we do not have 1 million years to a few million years to recover it, correct? So that's why we are turning to renewable energy, for example, wind, hydropower, and solar, etc. So combustion, okay? So combustion is the greenhouse gas emission important contributor. It is, sadly. And combustion is also used to convert the energy to, for example, electricity. So renewable resources actually cut down the carbon emission. So basically, if you use wind, solar, so basically you do not have you have very minimum carbon emission. But the problem with renewable sources is the intermittency. So what is intermittency? Basically, you have to depend on the availability. So for example, solar. So solar, you can only have maybe in Taiwan, you can only have maybe 8 to 10 effective sunlight, 8 to 10 hours of effective sunlight. So what about other hours? What about during nighttime? Correct. What about during nighttime? So during nighttime, there is no solar, and the wind is also the wind, because once they generate the electricity, it will straight deliver to the grid, to the electrical station, and then transfer to your home, to the places that we are using. But this renewable energy, they can only deliver at the capacity might fluctuate. So that's the problem with the renewable sources. So, and also one of the issue is that, another major issue is that the conventional industrial burners are actually very difficult to replace. let's say, for example, we know that in Kaohsiung, in Tainan, there are a lot of conventional industries. So a lot of them, you still use those industrial burners maybe 20 to 30 years ago. And if you want them to change all of them, it's actually impossible due to costing issue, due to a lot of issues, okay? And now, the world globally, now we want to achieve the zero carbon emission target in 2050. So the usage of the alternative carbon-free fuel is actually necessary. So after covering on the energy issue, so now we are going towards the shipping sector. So we know that Taiwan is one of the very famous shipping sector country. Okay, so basically it transports, shipping sector alone transports 80% of world trade by volume, just shipping sector alone. And it contributes to the 6th highest carbon emission worldwide. So it is after, I think if I'm not mistaken, it's between Japan and Germany. Just one sector. It is comparable to a country. So that's why carbon cuts are very important in the shipping sector. And you can see from here, this figure on the right here. So this is a figure of the International Maritime Organization. So basically they have already set this target to go to 2050 to have a net zero. Actually, there's not net zero, but every other company is pushing for net zero. You can see from the gray is going lesser and lesser, and until 2050, basically you cannot see any gray gas here. Okay. So you cannot see any gray gas here. So 2030 is actually the midterm decarbonization deadline. Okay, so it's around 8 years from now. And you know that the 28 years from now, all of them have to have at least 40 to 60% cut down in carbon dioxide. What does it mean? Meaning that all of the ships, doesn't matter from cargo, for cruise, cargo, okay? So long as you are a shipping sector, basically you have to cut down at least 40 to 60%. Doesn't matter you are using biofuel, doesn't matter you are using ammonia, doesn't matter you are using hydrogen, you have to at least cut down at least 40%. And Maersk's liner, okay, also one of the world famous transport liner, it plans for the world first carbon neutral liner in operation in 2023. And it aims to cut down at least 60% of the carbon reduction by 2030. And 2050, it aims to achieve net zero carbon emission. So it's actually very, very challenging for this sector, shipping sector. So that's why we need to keep this in mind. So there are actually 4 critical questions by Stephen Chu. Professor Stephen Chu is actually the former energy secretary in the United States. So our current hydrogen source is actually derived from natural gas. So this is actually not ideal. So basically you're just converting natural gas to hydrogen and then use it again. So basically it's very, it's not ideal at all. And second and third is actually linked together. We do not have a very high density storage. Okay, we do not have actually high density storage. And third is the distribution infrastructure. We are still very lacking on distribution infrastructure. And the fourth point is the fuel cell maturity. Fuel cell has been rising up maybe 10 years ago, 10, 15 years ago. But is it mature enough? No, it is not. Because of many issues, okay? And during this pandemic, actually the fuel cell, what do you call it? Some of the original materials, some of the materials for fuel cell actually have been growing in the price exponentially. Maybe last time you can buy the fuel cell materials, maybe it's like 500 USD per kilo, and now it's about 2,000. It's just in this 2 or 3 years time. Therefore, there's another an efficient hydrogen carrier, which is ammonia. So ammonia, it has an N, okay, bonded to 3 H atom. So you can see that this molecule itself, it is also carbon-free, correct? So when this is carbon-free, efficient hydrogen energy carrier, and so it is a very good promising alternative fuel. So it has a very high energy hydrogen density per unit volume than liquid hydrogen and also metal hydrides. So we can refer to the table on the right hand side. You can see that the H2 content is basically the highest. It is higher than methanol, ethanol, and gasoline. Despite the volumetric energy density is lower than these three, okay, but it is still higher than hydrogen. So per meter cube, it can deliver more energy than the hydrogen actually. So it also has some of the advantages over liquid hydrogen. For example, it consumes lower storage space, lower storage pressure. So for hydrogen, you need to have about 700 bars for the storage pressure. So for ammonia, you only need about 8 bars. And the liquefying temperature, oh, I think I did a typo there. So liquefying temperature is about negative 33 degrees Celsius for ammonia, but hydrogen is about negative 253. So can you imagine negative 253? So basically, when you transport the hydrogen, it is always there's always the there will be a lot of clogging problems, especially in warm climates such as in Taiwan. So ammonia, in a study, ammonia has shown to save about 10 and 47 times in the storage and the transportation cost compared to hydrogen. So a little bit based on a little bit introduction also on ammonia. So ammonia is created by a Haber-Bosch process. It's a very famous process. So it's created about a century ago. So this is the Haber-Bosch process reaction, N2 plus 3H2 to 2 ammonia molecules. However, this is a very high temperature and high pressure process, even in the presence of a catalyst. And the main usage is actually used as a fertilizer. So without ammonia, basically we might not even be here, because it has been used to feed more than half the population currently. And take note that the current distribution infrastructure, okay, worldwide actually exceeds 100 million tons per year. 100 million tons per year. So if we were to develop ammonia, if we were to further develop ammonia, actually we just have to use a very minimal investment, and also we can use it very confidently, okay, because it has already been there. It has already been there, okay. So, and also it is proved to be slightly safer than hydrogen because of the lighter density. So it can, if there's a leakage, it can dissipate to the air. So for the pungent odor, you can just smell it, many meters away, okay? And also it has a very narrow flammability limit. So it is not easy to ignite. So today we also cover on the shipping sector. So in shipping sector, it has already shown to as a promising alternative fuel, because the related safety, because actually in the shipping, ammonia has been used in the shipping sector as to transport between different continents or countries. So the related safety is actually an industrial practice in the shipping sector. So there's always a challenges. So pure ammonia combustion, okay, there are basically two main problems. There are two very big main problems. One is the low laminar burning velocity, which it LBV here, okay, because of the low reactivity and high auto ignition temperature. So remember in the introduction on the ammonia, we actually mentioned that it is safe, okay? But however, when we wanted to use it as a fuel, we want it to be reactive. So it's very contradictory. But we can see that from here, from the right-hand side here, the flammability limit, okay, you can see gasoline is 1.4 to 7.6. But ammonia, the flammability is actually relatively high, and it's actually very narrow, the flammability limit. Compared to hydrogen, 4 to 75 is already flammable, but this is 16 to 25. And the auto ignition temperature compared to this conventional or common fuels is actually the highest. So it's actually quite hard to ignite to reach auto ignition temperature. And then on the graph on the right hand side, bottom right here, so you can see that actually most of the time the burning velocity of pure ammonia and air is about less than 10 cm per second. Okay, per second. So if we compare to these methane air flames, it is less than 20% of the methane air flames. And also we know that the laminar burning velocity, LBV, actually decreases with the pressure. And if you can see from here, we changes the equivalence ratio. Basically, the LBV does not actually change much. So this is actually very bad news for combustion industry. If we wanted to use, because if the LBV decrease with pressure, basically we cannot do much. Okay. And this is only 10 cm per second, so it's very quite low. And the second major issue is that high fuel NOx emissions. So this is the overall reaction of the ammonia combustion. So we have ammonia reacting with oxygen to form nitrogen and water. That's the ideal case. Okay. However, our life is never ideal, right? So NOx is actually inevitably produced in the actual combustion case. So it does not matter how good is the theoretical nitrogen produced, but we always produce NOx in the actual combustion of pure ammonia. So here, in order to tackle these limits, I introduced some strategy based on some of my research. For the low LBV, so there are basically two strategies to tackle it. One is to improve the oxygen content. Okay, so oxygen content, if you can see here, okay, this bottom one is the ammonia A, and then the blue color one is the increasing oxygen content in the air being flow inside to combust with the ammonia. And when we reach zero, when the oxygen content reach 0.35 in the air being fed in, so we can reach very similar combustion performance similar to the methane air flames. So methane air is being actually around here, if you can see, is actually very close or actually slightly higher than methane air flames. So this is one of the strategy. And the second strategy is the additive fuel addition. So for example, other additive fuels such as methane and hydrogen can actually increase the LBV. So this is the second strategy. So let's say this is ammonia air, and then this is the ammonia methane, and this is the ammonia hydrogen. Okay, so these two are actually quite effective in this case. Okay, and then so for example, in the future slides, we have the stoichiometric fueling and fuel rich conditions. So stoichiometric is when the ER equals to 1, and then ER less than 1 is fuel rich, ER greater than 1 is fuel rich. So moving on to tackle the second limit, which is the high fuel NOx emission. So they are basically high fuel NOx emission. There are basically more strategies to tackle with. So we can burn under the fuel rich conditions. Okay, we can also burn under pressured condition, burn with steam, and also add in secondary fuel. So for burning under the rich condition, okay, burning under rich condition, you can see from here, this is the ammonia air flames combustion emission profile. So we can see that the NO actually peaks at about ER equals to 0.9 around here, and negligible around 1.3, somewhere around here. However, the unburned, when we burn at the fuel rich condition, this is when ER exceeds 1. So the unburned NH3 view increases suddenly, because the ammonia cannot fully react with the air. So we will have a waste over there. So, and if you burn under pressure conditions, so we can actually halve the NO. So it has shown to halve the NO from 1 to 5 bars, just 1 to 5 bars, we can halve the NO because of the OH radical reduction. And third is to burn with steam. So steam has also shown to increase the NO consumption for ammonia air flames. And the fourth strategy is to add in a secondary fuel. So the other additive fuels such as methane and hydrogen can actually decrease the NOx effectively because of the competing reactions. Okay, so why do we choose methane and hydrogen in this case? Because methane is actually very common and is also quite commonly used in the industry. And second, hydrogen. There's also hydrogen is as we mentioned, is also a very popular carbon-free fuel. But also, we can actually crack the ammonia into hydrogen as well. So in these strategies, we focus on the ammonia hydrogen and ammonia methane in this ammonia combustion. So actually a wide range of ammonia combustion studies, including kinetics, NOx, rich lean burn, ignition delay, have already been studied, okay, until about 2010s. So, however, an accurate model is still lacking to predict all of these performances. And most methods can only solve one single issue. Just like, for example, if we add steam, can only solve one issue. So in the previous slide, okay, so if you still remember, additive fuel strategy can actually solve both issues simultaneously. So in the following slides, we will target on the additive fuel ratio and also pressure towards the LBV and NOx emission in these mixtures. So just bear with me a while because it's quite textful. So when we have NH3 and ammonia and hydrogen combustion, in terms of the LBV, okay, the burning velocity, actually it increased over the wide range of equivalence ratio and the entire hydrogen range. So it has actually a very, very similar trend as the ammonia air. So because remember, when you add hydrogen inside, you will increase the reactivity, okay? And these are the three reactions that are dominating in the ammonia methane combustion. However, the burning velocity decreases with pressures. Because of the N-based elementary reactions, they're actually dominated over the H-based ones. And the reaction between the ammonia and OH radical also preferred over the hydrogen. So in other cases, for example, the flame temperature and heat release, when you add in hydrogen, you actually get higher flame temperature and heat release rate. And then you can also decrease the ignition delay time. And at this pressure, 10 to 30 atm, actually the decrease is more, you can see a more significant decrease compared to the atmospheric to 10 atm. So move on. So for the NOx, okay, the NOx emission. So the NOx emission, when the molar ratio of it actually increases, it's not decreasing, okay? Why is it increasing? Because when you add the hydrogen into the ammonia, actually it increases the temperature. Remember, it actually increases the temperature. So actually it contributes to the thermal NOx. So ammonia is still NOx, but hydrogen is actually thermal NOx. Because the temperature will increase, so the NOx will actually be produced at a higher temperature more effectively. And this is based on the HNO and NH oxidation. So however, the NOx will actually be negligible once in the fuel rich region. Okay. So it is also very concentration dependent. So if you decrease the oxygen content in the combustion, you actually can decrease the NO production. So at high temperatures, this hydrogen actually introduce even more OH and O radicals, therefore contribute to the higher NOx level. And the NOx, one good news is that the NOx actually decrease with pressure. So at 10 atm, we will only obtain at about 5 ppm. So at 20 atm, we only obtain about 1 ppm. So this is considered good news for us. And also the studies also have shown that if we can add steam to this ammonia hydrogen combustion, we can also mitigate the thermal NO, which means that we can actually slow down or reduce the thermal NO formation. So this, instead of this N2 plus O equals to NO plus N, we will have this reaction forming, okay, this 2OH. So you might have a question, why is it the OH radical and this OH radical, isn't it the same? But in this case, this OH radical is helping in the NO consumption instead of the NO production. So the NO consumption also is being used is through the NH2 mechanism for this steam. So now we have already finished with the ammonia hydrogen part. So now we move on to the ammonia methane combustion. So similar to the ammonia A and ammonia hydrogen, the ammonia methane, the laminar burning velocity actually also increased over the wide range of equivalence ratio and also entire methane range. However, it is in this ammonia methane is actually very sensitive to the methane addition ratio. And also the addition of the C component here, it actually complicates the reactions. So for example, in the previous slides, in the ammonia methane, ammonia hydrogen, it only enhanced certain reactions. But in this ammonia methane, suddenly we have added, this reaction still remains important, okay, for all the ammonia mixtures. But however, suddenly there's a carbon-based reactions coming out. So these carbon-based reactions will become more and more important. So under fuel-rich conditions, the flame propagation actually is dominated by the methane chemistry instead. Okay, it is because for the role is quite different. So we'll discuss it later. And the LBV is also decreased with pressure because the most important is that it is due to the increased unburned mixture density. So without the pressure, okay, at normal atmospheric, this part of the reactions are actually quite significant. Okay, when we increase with the pressure, so suddenly this three-body, the CH3, this CH3 reactions, okay, will actually gain more importance, and also this CH4 reaction will gain more importance. So this pressure will actually give it more responsive towards the NH3 and the hydrocarbon species. So in the fourth part is that the NOx. So when we consider ammonia methane combustion mixture, we have to consider additional gas, which is carbon dioxide, because we have carbon, right? So after we add in methane contains carbon. So now we have to deal with the carbon again. So, however, when we have the ammonia ratio, okay, when we have ammonia ratio greater than 0.6, so which means that when the methane is 0.4, around 0.4, the carbon dioxide actually is halved compared to the methane air flames, and the carbon monoxide actually decreases. So, and when you increase the methane ratio, you can also decrease the NOx. So this is a very fun part to tune with. So that's why we are in it for this understanding and also the research. And also, however, it is shown that the methane has the complete oxidation for all equivalence ratio. Doesn't matter whether you have fuel lean, fuel rich, or stoichiometric. The methane is completely oxidized. So there's a very critical part is this, when we deal with the equivalence ratio, this is to take note with, when we have ER greater than 1, okay, which is a fuel rich region, we have the increased CO production. If we have ER fuel rich and stoichiometric, we have the increased carbon dioxide. However, for fuel lean and also stoichiometric, we have the increased NO production. And the fuel rich can actually reduce the NOx effectively. Okay, so however, the good news again is carbon monoxide and NOx actually decrease with the pressure. And NOx has shown higher sensitivity to the pressure than carbon monoxide, which means that if we increase the pressure, NOx will decrease more effectively than CO. Okay, so this three-body reaction H plus O2 plus M equals to HO2 plus M, basically it suppresses the OH radical production. So NH plus NO equals to HNO plus H at this high pressure. Okay, so after that, we also consider the steam addition. So steam addition in this ammonia methane is actually slightly different than the ammonia hydrogen. It is no longer increasing the NO, but increase the NO. However, when you add steam inside, it actually decreases the carbon monoxide production. Okay, so we can see that all of these reactions, the promotion reactions, and this NO consumption is again through the NH2 mechanism. Okay, so other effects would be, for example, when we add in methane, it can increase the flame temperature and also decrease the ignition delay time with temperature and pressure and the methane proportion. So for me, this is some of the preliminary findings. So basically, all of these few slides are actually the findings from other people. So actually, I also reviewed this other people's works to derive at this slide. Okay, this is a very simplified summary. So basically, we can see from here. Okay, so for NH3, so for ammonia, methane, and ammonia hydrogen blend, if we increase the proportion, fuel proportion, and the equivalence ratio, basically we can increase the laminar burning velocity. And if we increase the equivalence ratio and pressure, we can decrease the NOx production. So the take-home message is if we can conduct the combustion in the slightly fuel-rich region and high-pressure condition, actually they are very, very beneficial for maximizing the LBV and minimizing the NOx production. So this is the graph you can see from here. So we have the methane addition and also the hydrogen addition here. So now we have finished with all the technical parts. Now we move on to some challenges. So for these combustion models, so we can see that, for example, the Mathieu, Otomo, and Tian, okay, so basically they can predict the ignition delay, LBV, and NOx of the ammonia combustion. And the Mathieu, Klippenstein, Okafor, and San Diego, they can predict pure ammonia, ammonia methane, and ammonia hydrogen, ammonia methane very effectively. However, if you find that there's one problem, is that there's no one model can unify all of this research together. Previously, we mentioned that, for example, on ammonia combustion, you have to use 3 models in order for these three different parameters. And then now you have when you have 3, one pure methane, one pure ammonia, 2 mixtures, and you also have a few more the combustion models. So actually it is very difficult for it to incorporate inside. So for example, the hydrogen role, okay, so from the previous researchers, we know that hydrogen actually enriches the OH radical pool. Okay, so the only function is to enrich the OH radical pool. So it's not it is just enhancing. That's it. However, the methane introduces the hydrocarbon species, and you can think of it as a parallel oxidation of the individual fuel in the mixture, sharing the same radical pool. So that's why both of them, when you add them together, when you add into the ammonia, you can actually lower the NOx production. And also studies have also shown that the CN interactions are actually negligible in the ammonia methane. So we can see that now the current models are actually, the major challenge is that the current models are not capturing the reaction kinetics of these many species compared to the real combustion systems, and the applicability of a very accurate reaction model towards multi-parameter still not realized yet, and we are still on the way. So almost to the end. So we have the ammonia color codes. Okay, so the very big figure here illustrates the green ammonia value chain. Okay, we have renewable energy, for example, solar, you have solar, tidal, and also the wind. When you have renewable energy and you can use it to do the electrolysis, and then you can produce the low carbon hydrogen. So low carbon hydrogen, and then you can combine with the N2 in the air, and then you can form ammonia. So ammonia can be used to fertilizer and storage, shipping fuel, and green chemicals. And basically, what are these color code mean? What does it mean? Okay, so brown ammonia actually is the current ammonia, which is derived from the coal gasification. And then the gray ammonia is from slightly cleaner fuel, natural gas reforming. And the blue ammonia is using the additional carbon capture and storage unit, the CCUS. So the green ammonia is the one that we are all talking about today, or green hydrogen. So green ammonia actually derived from green hydrogen, okay? So all of this, if you can see brown, gray, blue, green, basically are all the color originated from the hydrogen. So this is from the renewable electricity. And lastly, the pink ammonia. So the pink ammonia, the sun-killed bird is actually derived from the nuclear-powered ammonia. So actually, nuclear-powered ammonia actually shown to have a very low emission profile when producing ammonia. So future trends. So blue and this green ammonia are set to replace the gray ammonia in 2025 and 2030. Okay, this is the worldwide movement. So the stage movement is from the mixed combustion with coal. So this is the first step, and then slowly progressing to carbon-free green ammonia. And you can see that the time is actually ticking. It's 2025 to 2030. So 2030, our ammonia has to switch to green. Okay. So this actually demands a very strong collaboration between industries, government, supply and demand country. Okay. So we'll talk about the supply and demand country later on. So therefore, in order for this successful large-scale reformation to occur, okay, so global efforts involving regional, intercontinental, okay, accelerate the ammonia reformation as fuel in the various industries. For example, in the regional, for example, in the EU, okay, so many countries in the EU actually pushed for this ammonia to be this promising alternative fuel. So intercontinental, we have Asia, we have Southeast Asia, East Asia, Southeast Asia, and also Europe. There are a lot of countries that are joining in this movement also. And then move on to a very general part is that public perception, risk, health, safety regulation, advancement, infrastructure developments, material resistance to ammonia corrosiveness have to be the research also have to be conducted and also need to be to educate the public, okay, on this public perception. So the current and future directions for ammonia. So NH3 can actually be produced renewably. So further improvements on the low LPV of ammonia combustion and NOx generation are needed. The detailed chemical kinetics also needed. And lastly is the molecular understanding to practical application in the combustion systems before the commercialization of all of these blends. So today we can say that this blends is good, but we need to understand from molecular all the way to the practical side, whether this is feasible or not. So this is actually obtained from the Royal Society, okay, from this report. So if you can see from here, this is the current ammonia transportation roadmap. Okay, before all of this green ammonia or before all of this ammonia thing come out. Okay, so you can see that this region, okay, this region, I think it should be in Japan. Okay, it should be in Japan. So somewhere here we are. Taiwan is somewhere here. Okay, so this is Malaysia. So Australia is here. So we can see that a lot of countries here are actually very, very, very active, especially in the Europe. Okay, especially in the Europe. So now there's actually two paths. One path is that the ammonia is being produced in this Australia, because they have very vast land, okay, and also very good renewable energy sources, for example, solar. So they can actually, the target is to supply to Japan. And second, to supply to Singapore. So Taiwan is actually in between Australia and also Japan. and they can actually do the docking here. And then now there's also a second part is that the Saudi Arabia is also joining in this game, okay, this very large game, okay. So Saudi Arabia, because you know Saudi Arabia is producing petroleum, but the petroleum can no longer, they have to slow down the petroleum, okay. So when they slow down petroleum, so now they change to produce ammonia, okay. It doesn't matter how you produce the ammonia, as long as your ammonia is green enough, you can actually transport over here to the EU region. So the EU region, because if you produce ammonia from here and you transport all the way to the EU, it's actually too far for them. So therefore, the Saudi Arabia can transport to the EU region. And also, one of the things that you can see is that if you look at these ports and all of these facilities, there are a lot of facilities worldwide, okay, to support our 100 million tons per year of ammonia distribution infrastructure. But then, if you compare to hydrogen, maybe hydrogen is not even 1/10 of this facility. So therefore, we are saying that, okay, so therefore we need to coexist, okay, coexist with all of these facilities. So, and then this is the current microgas turbine, okay, used in Japan, okay. You can, if you look at all of these ammonia relevant papers, most of them also will put this figure. This is a figure that they are actually demonstrated successfully to produce electricity from ammonia. So ammonia power generation in Japan is actually already quite successful. And then this is the concept for from my previous group to produce or to use ammonia in the household, in the commercial, in the household electricity production. Okay, just a nearby. So we don't need to have a very big electricity generator. You can just household small scale, and then can distribute to the household. So so now we look at this Taiwan 2050 hydrogen application development technology blueprint. Okay, so this is launched, I think, this year. Okay, renewed this year. Okay, so hydrogen will stand at least 9 to 12%. Okay, by that time. So 750 million tons by 2050, and ammonia stands at about half, 115 million tons. And also the import of this fuel actually stands about 75%, because Taiwan actually cannot produce enough for self-use. So actually we are still importing. So the three directions of this Taiwan strategy is that they strengthen technology applications, complete transportation and storage infrastructure, and also expand the hydrogen import sources. Okay, so summary and future perspective. So I think it should be the last slide. So conventional fuels, they lead to a lot of pollution and environmental problems. So ammonia as a zero carbon fuel are actually very highly sought after. However, it is limited by the low LBV and high fuel NOx emission. So hydrogen and methane are studied as an additive fuel in this case. So it actually decreased the LBV, increased the LBV and decreased the NOx for both mixtures. And slight fuel rich and pressure conditions are actually good for maximum LBV and minimum NOx. So take-home message is there are two take-home message. The coexistence is the key. Okay, we have to coexist with the ammonia transportation or distribution infrastructure. We don't have to rebuild again, okay, from scratch. So that's why we mentioned about the monkey, remember? So that's why we coexist with it. And the future is actually already derived from the past. Okay, thank you for your attention.